Before I go further into the discussion of particular examples of different spin representations of the homogeneous Lorentz group, I want to drop back and look at the Lorentz group itself as a set of transformations as opposed to the Lorentz algebra. We have extensively discussed this Lorentz algebra and the transformations that it generates. In particular, we know that for any transformation, the commutator between m mu nu and any object, let's call it b lambda, which is a vector, takes this form here. Now you'll notice here that b first takes on the index mu, and b then takes on the index nu with a minus sign in between, an IH bar here, and the g has the indices lambda and nu first, then lambda and mu second. So the order of these is important, and we're trying to be very careful with our signs here. So now we want to use this commutation rule and take this that comes from the Lie algebra in general. And remember here, B is a general object which could be a position vector, a momentum vector, or electromagnetic field potential. It could be any of these vectors here. We want to use this commutation rule now to see what happens under a transformation in which we take a vector, b lambda, and transform it into a new vector, b lambda prime, by acting with two exponentiated Lorentz transformations. We have here, it's a little bit difficult to read, a 2h bar in the denominator here and a 2h bar in the denominator here. The h bar, of course, cancels the units of m, which has the dimensions of angular momenta, and if we were to let h bar equal to 1, it would mean our units of m are in angular momentum units of 1. The 2 arises from the fact that the eta alpha beta contracted with m alpha beta has two terms. One when this is in one form, and one when it's in its symmetric or reversed form. So we must take 1/2 of that in order for eta to have a meaning that's a little bit more meaningful. Symbolically, we're saying b prime is equal to a transformation u, b, u minus 1. Well, how do we do this? Well, we assume that this eta, for the time being, is going to be an infinitesimal transformation. As an infinitesimal transformation, we can expand the exponential as 1 plus I over 2h bar, eta alpha beta, m alpha beta. Here we have the b lambda. There are no higher powers of eta because remember eta is to be thought of as infinitesimal. Over here you'll notice that there's a minus sign as opposed to the plus sign here because this is the inverse transformation, u, b, u minus 1. Therefore this is 1 minus I over 2h bar eta mu nu, m mu nu. Now this is something that we have to be very careful with various indices, in both special and general relativity. It would be very dangerous for us to write alpha beta here and write an alpha beta also over here. Anytime a summed index occurs one place in an expression or an equation, we must be very careful to use another letter to symbolize that summation in another place. So you'll notice I've used alpha, beta, mu, and nu, and likewise carry that forward to here. And that all is different, of course, from the index lambda. Anytime you have a summed index like this beta, I could replace it by anything else, like a zeta or some other index, but that's not necessary. If I expand this expression now, of course, I get a 1 and a 1 with beta lambda. Then I get an I over 2h bar, eta alpha beta, times two different orderings. One ordering where m alpha beta multiplies b lambda in one direction, and then the negative of where m multiplies b in the other direction. Of course, the second term has eta mu nu times m mu nu. I therefore change in that second expression, in order to pull outside of the expression the eta alpha beta, I change this back to an alpha beta and an alpha beta. that allows me to write this as the commutation rule of m alpha beta and b lambda. This is a very important step, so if you need to, stop it here and look at that just for a moment. I then get a cross term here, which of course will be of order epsilon squared, and so all other terms are of order epsilon squared, and since epsilon is considered to be extremely small compared to 1, I can neglect all higher powers. Now you can see why the group and the algebra are so closely connected. This is a very important position that we're in right here. That's to realize that after we do the transformation that is generated by exponentiation, i.e. the group transformation, we are led to lowest order to a study of the commutators, of the thing that is being transformed by the transformation generator that's doing the transformations. That commutator, defined up here, then is replaced at this point, so we now substitute this right in here, and we get I over 2h bar eta alpha beta IH bar times the commutator, which is G lambda beta times B alpha, and then it'll be beta over here, where this is G lambda alpha. Of course, I times I gives us a minus. The H bar cancels with the H bar, and that disappears. And we're left with an eta alpha beta times a G here, and another one times a G over here. So actually what this does is, if you look carefully, this beta is summed with the eta beta here, and that raises this index to a lambda. Remember, G contracted with any index raises or lowers that index depending upon whether the G and the other index is upper or lower, contravariant or covariant. So this leaves us in the first term with an eta lower alpha upper lambda, because this beta has been raised to a lambda, times B alpha, minus eta, and now we have, if we think of this alpha here, the alpha has been raised to a lambda, so we now have an eta that's been raised to a lambda right here, and the beta stays where it is, times B beta. Now we can rewrite that, and you'll notice that the 1/2 is still out front, and this is where the 1/2 disappears. Since eta has to be antisymmetric, since it's contracted with an antisymmetric matrix, only any symmetric part that it contained would disappear instantly. So we know that this is antisymmetric under two lower indices, and therefore between two upper, and it's therefore also antisymmetric between the upper and lowers if these are interchanged. So what I can do is, here I have the alpha and the lambda, and I can change I can invert the lambda and the alpha, and since this is antisymmetric, it will give me eta lambda alpha times B alpha. Well, this is eta lambda beta B beta. These will then have the first term and the second term will then have the same sign. I have a 1/2. I have two terms. The two terms will be identical, both of the form of eta lambda beta B beta, and therefore that will cancel the 2, and now I only have one term, which is of this form right here. By separating out another term, which is a simple Kronecker delta function, delta lambda beta times B beta, we can then separate these two terms into a tensor term in the front that multiplies B with a beta in front. I want to make sure that the sign was followed here carefully. So if you look at this, we have an I times an I, which gives us a minus, and we're left with the term 1/2. The H bar is gone, and this minus sign here acts on the first term and gives us a negative sign. The minus sign hits this because of the parentheses. The second term is actually positive. So we have a positive term that is eta lambda beta, b beta. What I do with this first term that's negative, by interchanging lambda and alpha, I change this from a minus to a plus term so that both terms are positive. And they have exactly the same form. The only difference is this one has a summation over alpha. This one has a summation over beta. So I make both of those terms, I change this index alpha to an index beta, and then I get two identical positive terms. That cancels the 1/2 here, and I end up with this expression. We want to be able to pull the b out of this term here and here. And we can do that by writing the first term, b lambda, as delta lambda beta, b beta. Now you'll notice that when we did that, we chose the delta lambda beta, we chose the lambda to match this lambda here, and the beta to match the other index that's summed over. Otherwise, we wouldn't be able to pull b beta out of the entire expression. So this is what we were looking for, and this is our result that is so important to us at this point. We continue here with the homogeneous Lorentz group transformations, and we're looking at a transformation that transforms a vector b into a vector b prime. We're looking at this in a situation where it was generated by an infinitesimal transformation. In other words, the coefficients, eta, alpha, beta, were extremely small compared to 1, that is infinitesimal, and we just obtained the following result. That our transformed vector will be equal to a delta lambda beta plus eta lambda beta times b beta. Then this is the lambda beta matrix element of the matrix delta plus eta, which we can exponentiate and make finite in the following way. In other words, what we're saying here is imagine that this transformation right here is the expression 1 plus eta, and this is the lambda beta matrix element of the expansion delta plus eta. And since eta is infinitesimal, if we were to repeat that again and again and again, it would take the form of e to the power eta. Now you remember e to the eta, if eta is infinitesimal, is equal to 1 plus eta. Because eta squared over 2 factorial and so forth will disappear if they're infinitesimal. Therefore, repeated actions of that infinitesimal transformation will give the lambda beta matrix element of this exponentiation. We're going to write that as a capital lambda. That didn't turn out too well. It's a capital lambda with lambda, the lambda beta matrix element, times b lambda, where lambda is the Lorentz transformation or the rotation. Okay, let's first take a situation where we're going to choose the eta to have a particular form. We're going to take eta to have the form zeros, 0, a minus 1 here, a plus 1 here. Remember, it has to be antisymmetrical. And you can see that since this is the 0, 1, 2, 3 columns, 0, 1, 2, 3 rows, that this is the 1, 2 element and the 2, 1 element. So this is going to be a rotation in the xy plane. Let's prove that that's true and see what we actually get. So we're actually only going to look at this piece of the matrix element because everything else is 0. Therefore, when it's exponentiated, we will get a 1 here and a 1 here and a 1 along the diagonal, plus these infinitesimal changes. So we take e to the, now I'm going to write a parameter eta This is just an eta Greek letter representing a parameter like theta or something else that we would use to parameterize this transformation, times a 0 minus 1, 1, 0. Well, let's expand this and see what we get. First of all, you get the identity, 1, 1. Then you get eta. This looks like an N, but it's supposed to be a little eta, a little tail on it. 0 minus 1, 1. Then eta squared over 2 factorial, eta squared over 3 factorial, eta squared over 4 factorial, and so forth, to the various higher and higher powers of this matrix. Well, what is the square of this matrix? Well, obviously, this times this gives us a minus 1, 0, 0, minus 1. That's because this times this gives us a minus 1, this times this gives us 0, this times this gives us 0, and this times this gives us minus 1. So, if I take this times this and to get the next power, then you can see I get a 0, 1, minus 1, 0. Then finally at the fourth power, I get this squared, which becomes a plus 1, plus 1. This thing then cycles every fourth power, since the fourth power of this little matrix is equal to the identity. Every fourth power will be equal to the identity, and we'll cycle exactly back through the same sequence. Now, writing this in a matrix form, let's look first at the diagonal. You'll notice that the diagonal terms here, 1 and 1, only appear in every odd power, or excuse me, I should say even power. The 0th power, the square, the 4th power, and so forth. And so what are they? We will have a 1 plus eta squared over 2 factorial minus 1 plus eta to the 4th over 4 factorial with a plus 1. So we get here for this first component of the matrix this plus this plus this, which leads us to a 1 minus eta squared over 2 factorial plus eta to the 4th over 4 factorial. Likewise, we get exactly the same thing down here. That's the 1. We get a minus 1 again times eta squared over 2 factorial, so that becomes here. Then we get a plus 1 times eta to the 4th over 4 factorial. It becomes right here. It's important to understand how we're breaking this matrix out by identifying these various pieces. You can cut this matrix up into a form like this, and it might be easier to understand the four parts. Okay, now what are these off-diagonal terms? Well, it's a 0 here, and here we have an eta times a minus 1. Well, there's minus eta. Well, in this opposite part, we have a plus eta. Then we get a contribution, no contribution at the square or the fourth, but at the cube term, we get a plus eta cubed over 3 factorial, or a minus eta cubed over 3 factorial. There's the plus eta cubed over 3 factorial, minus eta cubed over 3 factorial. That gives us this matrix here. Well, we can see the pattern from the little bit that we've presented so far. And the pattern is very simply. This is the cosine of eta. This is the negative of the sine of eta. This is the sine of eta, and this is the cosine of theta. So we end up with a transformation, to see what it actually looks like, of cosine minus sine, sine, and cosine embedded in this 4 by 4 matrix. This just kept it a little bit easier to look at. And so that gives us now the components of this large matrix lambda, which is our set of all rotations and Lorentz transformations as contained in the homogeneous Lorentz group. The procedures for doing this are very universal and extremely important. So it's critical that a person sit down from scratch with the commutation rules that we began with on the last page and derive this with a clean sheet of paper in order to feel comfortable, because this is the way we always make the connection between the Lie algebra and the Lie group. We now are going to look at the same type of transformation, not with a rotation, but with a Lorentz transformation. In this particular case, we take our eta to be of the form 1, 1. Now we do this because it looks like it's not antisymmetric, but it really is, because this eta has one upper and one lower index. Therefore, if we lowered one of these indices, then we would get a -1 here, whereas the other, when we had two spatial indices, we would have two changes in signs. So if we take now e to the eta in this form here, and we are only going to look at this one part of the matrix, we would get, when eta is equal to 0, an identity operator. Then eta times this, plus eta squared over 2 factorial times this, plus continuing on here. It's very straightforward then, as before, to take these terms and sum them. We can see that the diagonal parts, again, only occur every other one, but now we do not have a sign inversion with every change in order. So we have a 1 plus eta squared over 2 factorial times plus 1 plus eta to the 4th over 4 factorial, and we have that on both the upper and the lower piece of the diagonal here. So we get a 1 plus eta squared over 2 factorial here, here, and then for the odd terms, we get eta and eta. There's the eta and the eta right there. An eta cubed over 3 factorial here and here. And likewise, this continues on. It just takes a moment to check back through your books in algebra to realize that the trigonometric function here is the hyperbolic cosine. Now, we often write the hyperbolic cosine, COSH, is just CH. And the hyperbolic sine is, rather than writing SINH, we write it as just SH. So this is the hyperbolic cosine and sine of eta, as I've expressed right here. And therefore, our Lorentz transformation takes this form right here of the hyperbolic cosine and the hyperbolic sine. It's really important, as I mentioned, to review these and to make sure that one can go through them, keep the signs straight, and realize that this all follows from the commutation rules in the algebra to generate these transformations on the group level. We'll be using these group transformations later on.